forward. If you wish, you could do it at home. Well, why not do it? Okay. But the derivation is not so important, and that's why I skip it. Of this part, this is doable. Easy to do. Okay. Now, what does this mean? Essentially, the effective potential. It says, look, you've got one Coulomb attraction term over here, and there's a repulsion term over there. Right? Now we have a negatively charged electron and a positively charged nucleus. Where does the repulsion come from? If you think in terms of classical mechanics, could you figure out some way of, this electron is rotating about the nucleus? Centrifugal force. Good. So you could treat this as kind of a centrifugal force. But of course, this is not classical mechanics, right? And the kind of, this essentially the repulsion comes because of something known as the Pauli exclusion principle, which does not allow two fermions to coexist in the same space. And all these protons, neutrons, electrons which have half integral spin. Now, I'm talking of things that perhaps you know, perhaps you don't. But, and definitely I'm not going to teach spin in this course. But the things that have half integral spin, those are known as fermions, and they behave Fermi-Dirac statistics, which means not more than two fermions can be accommodated in one spatial coordinate, because then the spin coordinate also comes in, which is either up or down for the case of electrons. But anyway, all of these coordinates, spatial plus spin coordinates, cannot be the same for any two fermions. So, if I bring the electron very close to the nucleus, that is not permitted as per quantum mechanics, as per the quantum mechanics statistics. Okay. This, therefore, is a repulsion. It's not exactly a repulsion term. It's this disallowance of the two fermions to come close. This term represents that. There's absolutely no reason for me to have any repulsion. Right? Okay. This doesn't happen if the value of L is 0. Right? We'll worry about why it doesn't happen. In fact, this could be a good thought exercise. So if the value of L is 0, this repulsion term goes away. You could think in terms of centrifugal terms, right? If you wish to think of this as a repulsion, think in terms of centrifugal. But actually, it's because of the Pauli exclusion principle, which also says that two electrons cannot be in the same state. Right? If they are in the same state, then always you show it like this, paired up and down spins. When I say in the same state, I say both up. You cannot have. So r, theta, phi and the spin coordinate, all four cannot be the same. Okay. In fact, there is a question in your tube which says show that the electron cannot come very close to the nucleus using Heisenberg uncertainty principle. Okay. Now, if that is the case, the way the potential would be plotted would be something like this. This is my effective potential V effective, and that's the radius. And for one of these cases, when L is equal to 0, it's going to be always attractive. So it goes something like this. It's a negative potential, right? And when L is not equal, so this is L is equal to 0. And when L is not equal to 0, and okay, for large values of R, I don't have to worry because this is a 1 by R square term. So for large values of R, this should be more or less identical. But at smaller values, the repulsive term starts to dominate because R square would be more dominant at closer distances. So when this takes over, there will have to be a minima. When this takes over, it will go positive. So repulsions start to dominate at very, very small distances, which is L not equal to 0 for that case. Right? Now, if I think about the wave function of hydrogen atom, one thing I know is that infinite distance, there should be no effect of the proton on this electron. So the wave function must go to 0 at infinity, right? And the other thing is this potential. This potential does not allow the electron to come towards the nucleus when L is not equal to 0. For L equals 0, this potential does allow it to come. It's an attractive potential all the way. So what I know is then that my wave function should be something like this. So for L equals 0, something like this at very close distances. So that's R and that's my wave function. And so that's L equals 0. And for L not equal 0, it should go something like this. And finally, it should decay to 0 at large values of R. So let me make this longer. Which color was it? At large values of R, all of them should decay down to 0. What happens in between is something that I cannot figure out without knowing the equations, right? So let me just write those equations. The equation that comes as a solution to the above Schrodinger, we wrote the Hamiltonian, right? So we can write Xi equals E psi and get that. So, no, did we write the Schrodinger? Yeah, we wrote the Schrodinger equation also. So the solutions that come out because of this, without much explanation, are n comma L. It depends on both two quantum numbers, one is L and one is n, and it's a function of the radius r, is equal to some normalization factor, rho, which I have defined already, to the power L, some polynomial L, okay, which is a function of rho, and it depends on the values of n plus L, and it also depends on the value of 2L plus 1. Don't even worry about what this polynomial is. In your maths course, you will be surely taught that. I already saw that today you are being taught orthogonal vectors. Yeah? Non-linear, linearly independent, that's what he said. Then I entered. Yeah, that is orthogonal vectors. Sure. Although you will have a much more rigorous treatment in maths, okay? So you will learn it much better. E to the power minus rho by 2. So this is the one that is giving me my exponential decay. This is a polynomial in rho or in R, whatever you wish to.